introduction. Thank you for inviting me here. I've been very excited this entire time. This is my first time out in this ecosystem. Oh, okay. Got it. Can you hear me?
Okay. How about that?
1 second.
Okay. Is this is good? Okay. Yeah, I was very excited to come here. I've been very pleased to see how much is going on in this ecosystem here out in Berkeley in the Bay Area more broadly. There's a lot of stuff that I've been learning here, and so I appreciate you all for coming and giving great talks and doing great research. Today, my talk is titled Utility Scale Quantum Computation with Qiskit. But today, more informally, I would say my role is to act as a Qiskit apologist. As many of you know that Qiskit has changed a lot in recent times. And hopefully today I can explain why these changes have been made and explain the new structure in a way that is more intuitive so that as you jump into it as either as a first-time user or somebody who is coming from the pre-1.0 era, you kind of understand how to navigate the new form of the code base. And I say this from a perspective of also having been frustrated, right? When I first joined IBM 2.5 years ago, I was using something like Qiskit 0.35. I started a project that to this day has not been accepted in journals. So, every few months we run experiments again. And I can't tell you how many times I've rewritten this code base. But what I can say is that indeed, after switching to 1.0 and using some of the new features, it actually has made the entire code structure a lot more simplified, although there may be bugs to deal with. I used to have this 10,000 line code base to do everything kind of manually, twirling, ZNE, all this error mitigation stuff you might be familiar with. Having it wrapped up is convenient. So I hope I can convince you of that today. The talk will be in two parts. The first will be a broad introduction to the structure of Qiskit, how we're thinking about it nowadays. And then the second part will be a little bit more technical. It'll be talking about things that we're calling Qiskit add-ons, which are these modular open source packages that allow you to do new things that are coming out of research papers just from a few months ago. And in fact, there are several people here who presented on things that have been featured in those. I believe, Osama, you presented about SQD, which is something that's now wrapped up. There was some talk here about these kinds of approximation methods in Qiskit. It's very similar in principle to what we have in operator backpropagation. So there's a lot of things coming out there. The final point I want to make is that as I'm giving this talk, of course, I have talking points, but I'm sure you have questions that are more important. So please feel free to stop me as much as you'd like, and I'll answer those over what I am talking about here today.
The thing so people can see.
Okay. Oh, okay, sounds good. Yeah, and then I guess I have until 3:15, so I'll stop then so people can leave if they have to, and then I'll stay and continue to talk with people, maybe present the rest of the material depending on whatever people want. So with that long preface, let's get started here. I don't think I need to explain anymore that we hope to use quantum computing for a lot of interesting use cases, but here's at least the IBM spin through these various working groups that I believe many of you are actually part of. They've released these 4 perspective articles in these different fields, some of which are now published as well. And so if you're curious about the perspective that we're coming at, the kind of problems that we're interested in, I highly recommend you check these articles out. And so we have these application use cases, but then the question is, how do we actually accomplish those applications? And so the way the mantra goes is that Qiskit plus QPUs is work. And so we have the QPUs, and Qiskit is kind of the underlying, maybe like the support structure for accessing those QPUs efficiently. We want to be able to build circuits. We want to do workflows through patterns. That's something I'll introduce. We want to be able to send information to the quantum computers efficiently. That's going to be through the runtime primitives. And finally, I'll talk about the add-ons, which are these modular packages for changing the structure of your computational workflow. It's not working. Okay, so what are Qiskit patterns? Qiskit patterns is just like a 4-step process, right? The first step is to map classical inputs to a quantum problem. This is when you do things in a chemistry problem like your Jordan-Wigner to qubits. Next, we want to optimize this for quantum execution. So this is where we pass them through what we call a pass manager for transpilation. And you can see there's all these different layers. For unitary synthesis, you do translation. And the farther you go down, the closer you get to the hardware typically. You want to produce a circuit that can be executed on the hardware basically as is. So it should abide by the native gate set, the connectivity, things like that. And then you submit them through primitives. And we currently have 2. the sampler gives you its samples, so you get bit strings back from it, and you get the estimator, which kind of wraps up this, the kind of easy step of converting bit strings into expectation values, but also has some other tools under the hood to help you out, such as, I don't know, estimating error bars based on like, sampling bit strings. It can also do some error mitigation for you as well. Yes.
Sometimes you can also add other observables or multiple observables. Can you do a group of observables here and it will automatically adapt the circuits to measure those? Or
Yeah.
they have to be all diagonal so you don't.
No, you can put whatever observables you want. And then under the hood, all it's doing is appending basis rotation gates.
Okay, it's doing automatically.
Yeah, but it just collects that information and makes it a little bit easier, right? Yeah. So things you could definitely do manually, but just takes care of it in a more human readable format. Yeah.
And if you do this on a real hardware, how many shots would I effectively use? Is it number of shots I ask or number of shots times number of observables?
It depends on how you input it, but probably you're just going to give the number of shots you want per observable. You can also specify the precision you want, and from there it can calculate how many shots you would need. It's just solving like it's just solving a very simple distribution. And so, yeah.
Well, I'm asking because at the end I am blocking machine. I want to know if I block it for 10 minutes or for 60 hours.
Yeah. I mean, that's a question that will be answered in documentation of exactly what is being, what does that value correspond to? But I believe it is going to be per observable. Yeah.
You know, the optimizations that might be done by the estimator. Is there much control you have over that?
The estimator nowadays should basically run what you give it, plus some of the things like the randomized compiling, the twirling, and maybe insertion of dynamic with decoupling. But it should basically run what you give it. Yeah. Now it gets a little bit more complicated when you have dynamic circuits, because how that's actually done under the hood is actually changing all the time, because we're catching up to what we want to do with it. But for standard unitary circuits, you basically submit what you want to run. Yeah.
The mitigation technique they are adding to the task manager runtime or into
It's-
the task manager?
That'll be in the execute step.
Oh,
You can set these options and it'll handle some of that stuff for you. Yeah. Okay, great. And then the final step is to do, of course, post-processing of your results. Nothing too special there. All right, so why do we divide this into patterns? I mean, your code is probably already written in such a way, but why do we formalize the structure a little bit more? The idea of course, is to have composability. The idea is we can take different steps and swap them out for other ones. We also still want to be able to wrap everything up and send it to somebody else and say, you can run and replicate exactly what I've done here. And we also want to abstract a little bit away from, literally gate by gate construction of circuits and observables. One very simple example is you can always measure in the X basis by applying a Hadamard. And we just want to abstract a little bit away from that, right? You can always add together your expectation values to get an energy of a molecule or whatever. And we just want to take a step away from that and think a little bit higher up the stack. So now what I'll do is walk through each one of these steps and kind of highlight the main classes and tools that we have, many of which you'll be familiar with, some of which will be new to the Qiskit 1.0 series. The workhorse of step one in mapping is a circuit toolkit. Of course, Qiskit.circuit.library allows you to create quantum circuits. And then in defining your problem, you also need to define your operators. And so there's this nice class sparse polyop. You don't want to save your operators as 2 to the n by 2 to the n matrices. So this is just an efficient way to specify them. And then Qiskit 1, there's a lot more support for classical logic in your quantum circuits. If you know about dynamic circuits, right, you do a mid-circuit measurement, you feed forward. In the near term, this allows you to do certain things like PhD state preparation very efficiently. And then it's going to be an ingredient in the long-term error correction. So if that's something you're interested in, these are now capabilities you have. But I should note that not all classical logic can be implemented on the device yet. That should be described somewhere exactly what you can do, but that's also changing over time. And then final point is that there's been this big focus on performance. So not a difference in how you use it, but maybe in what you notice as you use it. And so, something we talk about now is this 55% decrease in memory usage, supposedly over, averaging over some benchmarking protocol that they call bench press. You can find that on arXiv as well. So just some examples of building quantum circuits. You can still build them from scratch if you'd like. build your quantum register, add Hadamard's CNOT gates one by one to prepare GHZ state. You can import pre-built quantum circuits from a library. So this is for quantum machine learning, these ZZ feature maps, poly feature maps. And you can also import variational ansatses from scratch. This is the efficient SU2. So layers of CNOTs with rotations in between them. And then the next step is you want to specify the operator. What are you measuring? So you can specify polystrings. Another thing you can do is, so in encoding a fermionic Hamiltonian, you might know by hand through the Jordan-Wigner transformation that this is what my creation annihilation operators look like. And so you can build it by hand if you'd like. And then from there, it's quite straightforward to convert this into an e to the minus IHT. And you can also specify how you want to trotterize this, the time step, and it just handles a lot of that for you under the hood. Great. So the next step is optimizing the quantum inputs. And the workhorse here is going to be the transpiler. So the transpiler, the formal definition we go with is you're going to convert abstract circuits to ISA. I forget what instruction set to architecture circuits, I think. And it basically says, like, this is what we can run the device. It has native connectivity and the native gates. And so to answer your question, you're submitting basically something as close to the hardware as you can. And we've kind of redone the way that you can do transpilation. You might recall optimization level 1, 2, 3. That's still there to get these pre-built pass managers. But then built into that is also the ability to more easily swap in different passes in and out. And there are some that we have designed, some based on reinforcement learning for doing linear synthesis, routing, Clifford synthesis, for example. But I built my own pass managers that you can just slide in there very straightforwardly if you'd like. This is another thing that you probably don't notice as I don't know, it's like a new feature, but again, there's been a lot of effort to make transpilation way faster. And I can say this also from experience, having tried to run 100-qubit experiments a couple of years ago. This is something that a laptop overnight would take to transpile many tens of thousands of circuits. And now supposedly it's 16 times faster with 23% fewer gates compared to Ticket. I don't know how this is compared to Qiskit here. I don't really want to get into that, but it is faster than before and it's noticeable. I think so, but I haven't done it myself and can't explain that directly. Yeah. Okay. So this is just showing how this would be done, right? So in this case, the first block here, we are calling a backend. This is Sherbrooke, one of the really nice devices. You're generating this preset pass manager, and you're saying we're going to set to optimization level 3. For those in the know, this does a lot of optimizations, including like the stochastic Saber swaps. And the reason you have to put in the backend for the pass manager because it has to know the gates and the connectivity, and that's contained in the backend information. And when you run the pass manager on your target circuits, let me get the highlighter out. You see you produce this ISA circuit, and this ISA circuit is something that you can give directly and run on the device. Okay, there you go, ISA. Instruction set architecture, yeah. All right. You also have to be careful to apply this layout to the observables, because as you swap around your logical to physical qubits on the device, the observables also have to be swapped around. It's a very straightforward procedure. You just apply the layout onto the Hamiltonian to get the ISA Hamiltonian. All right. Now there's also a question of like which qubits you assign it to. Something that is just a fun little feature. I wouldn't say this is like, it's kind of hard-coded in a way, is that we characterize the devices based on looking for the best 1D chains we can find on these 2D devices. And we actually also save that information, so you can call it if you would like to map your problem to a 1D chain as well. So it's just like a fun little feature you have that also can be pretty helpful. And so you can find basically the longest chains up to 4, 5, 6, 7 to 98 qubits, I think, in this case here. And so what's drawn in red is this best 98 qubit chain kind of wrapping around the device here, or 96, I guess.
The metric you use to drive them?
This metric is the error per layer gate, the EPLG. This is what you see on the devices for EPLG for like the longest number of qubits. So it ranks the layouts by this metric.
Which is what some of the errors of the CNOT gates apply to those elements or something more complex?
It is, okay, so yeah, so the key, okay, I guess to start with, like, why don't we do some kind of randomized benchmarking or something and just quote that number? We used to. But then the observation was that if you run many gates in parallel, the performance overall typically degrades, right? You calibrate individual gates, but you run them in parallel. And so then this EPLG characterizes the average performance of a gate when they're being run in parallel in a 1D chain, which is typically, like how you would do it. So yes, that is the metric. It's more application oriented.
Do you experiments? Do you actually test it by running it, or do you?
Yeah, this is done in like calibrations, overnights. Yeah. Okay, great. Oh, I mean, this answers your question exactly. So they're showing these 2-qubit errors. You can see the EPLG for these different chains on this IBM Fez. Okay. Now the third step is to execute via the primitives. I kind of already explained this. Primitives have the sampler and the estimator, and what you're submitting the primitives with is Qiskit runtime. And so this is something that's designed specifically for interfacing with the IBM Quantum Cloud interface. And so this is something where you start to move away from like the device agnostic part of Qiskit, right? And so you might, I mean, I think you could build a runtime for accessing, say, Bracket or whatever provider you have, but this gets more specific to the IBM one. And I would say a key feature here is that there's different ways to submit jobs now. In the old days, it was you just submitted single jobs. And I remember doing this again for my case of 300,000 circuits, submitting like, was it 10,000 jobs or 1,000 jobs? And it's totally crazy. You have no control over when they're run. You don't know what the noise is going to look like over time. And there's also a lot of wasted time because every circuit you submit has to go through some classical processing before it actually runs on the device. So a lot of those problems are attempted to be tackled with this new way of doing things. You still have single jobs for your one-off test cases, but then you also have this batching when you know you're submitting many circuits in a row and you want to parallelize this classical compute. So the time between the circuits is as little as possible. So that's this batch mode. And then finally, there's sessions. And so this is where you get more interactive access with the device. And so you just book it the entire time. There's no circuits being interwoven between yours. And so this is good if you are doing, let's say, a variational problem where you're going back and forth, quick optimization, send new parameters. You could use sessions for that. Yeah. Yes. Or either of you.
So are you charged on the full time for the session, or only the actual quantum computing time of the session?
I think sessions you're charged for everything. So if you're doing classical computing and it's expensive, that's on you. But the batches, I think you should only be charged for the quantum time because the idea is the classical part is offloaded. Yeah.
It's like the reservation.
Yeah, it's like a reservation. Yeah.
So for this batching option, the short-term compilation time is no gain. Me as a user, I don't care.
Yeah. I think it's on like the IBM server. But you also have to be careful, like you can't offload too much because there's also like clock limits for the kind of classical compilation that'll happen in the background. So it is better to submit things as close to the hardware as possible. Yeah.
It can always be compiled to make it before it's submitted.
Yeah, exactly. And to answer the question or the point about a reservation, I mean, it's almost like that, but you don't get to choose your times, I think. I think you just say you request a session, and when you can get that session, you get it, and then things start to run. Yeah. Okay, so how does this actually look? Primitive. It's meant to be as simple as possible. So you initiate this sampler. You say this sampler is for this backend. You're going to run this circuit, and you might be familiar. You get an ID, you get your status, and then what it returns is the counts. And it built into the sampler here, you get things like dynamical decoupling, polytwirling, post-selection. These things are almost so vanilla in a way that we don't want people re-implementing them. But I think there's open research in these areas as well. And so you can also do your own twirling, your own dynamic decoupling. And if that's something you're interested in, I can talk to you later about how to do that in an effective way. And then here's the estimator primitive, very similar. There's also like optimization level for transpilers, there's resilience levels, and this sets basically different levels of error mitigation. And so it's contained in the documentation. There's levels 0, 1, 2, and 3. And you basically get expectation values. But then, like I said, you also get a little bit more wrapped up in it. Here you can get like the target precision. you can request more metadata, like to estimate the error bars on the expectation value and things like that. Yeah.
The previous slide for your sampler, what is the upper bound for your sampler number of qubits?
Qubits, that'll be just limited by the device. So, 127, 155.
I'm using sample states.
Well,
Can you do that?
well, you can measure from all the qubits simultaneously, but if you want, the density matrix, obviously that scales very poorly. But you can measure, in parallel all qubits. So you can get 127 bits from one execution of the sampler. Yeah.
You mean clusters of qubits, not all of them. That's mean that they have a circuit that uses all 127, not just clusters.
In one shot, you can get all of them. You can measure every qubit simultaneously. Yeah.
Give me the sample all the states to the 128.
No. So every time it samples, you get one bit string of 127 bits, and you can choose how many times you sample, 1,000,000 times. I mean, that's smaller than 2 to the 127, but like you are sampling from them all at once, if that makes sense. Yeah. Okay.
There's no limit on the how many shots I could.
You pay for it.
You pay for it. Yeah, you pay for it. There
Do
actually,
you have a limit?
I think there might be a hard limit. It's probably 10 million or 100 million.
Yeah.
If you really wanted to go around that, you could submit the same circuit multiple times. I don't know if I recommend that.
That's
Yeah.
fine.
Yeah. Okay. Oh, and this is just a description of what you have. So in the primitives, the estimator, you have suppression just like before, the dynamical decoupling, the polytwirling, but you can also have access to these other methods, twirled readout extinction for getting readout errors, zero noise extrapolation, and if you look around the documentation, you'll even find the experimental version of the probabilistic error amplification code or options. And this is what was used in the IBM's Nature paper where they did the utility, the 2D kicked icing model. That method is now wrapped up there, and you can also find that. Okay, so this is just an example of all the kind of utility scale results. Not all of them have used Qiskit 1 to be clear, but towards this effort of like basically increasing the system sizes that people explore with the devices so that we explore more scalable methods. Some of the ones that I've worked on here, if you'd like to talk about them more later, is this one, best practices for quantum error mitigation, this uncovering local integrability in quantum many-body dynamics, and finally this one on the right here for looking at long-range entanglement using dynamic circuits. I've already chatted with a few people about this work, so I'm happy to talk about that more after as well. And I guess there just continues to be more and more in this direction. Okay, so I do have a tutorial, but just kind of given time constraints, I think I'll just like walk through it. And if you're interested in it, just go onto this site and you can do it yourself. But the point of this tutorial is to introduce you to this framework of Qiskit patterns, this 4-step wave thinking. And the idea is to basically reproduce the paper that I just mentioned, this paper here, Evidence for the Utility of Quantum Computing Before Fault Tolerance. This is the one where they simulate the circuit of a 2D kicked icing model, depth 60, something like 2,600 gates or 2,900 gates, measure these multi-qubit polyobservables in different bases, and ultimately, give tensor networks a run for their money, although they ultimately came back with a laptop runnable method, right? But this, I think, is a very impressive experiment in terms of scale and something that before these tools would have been very hard to run. So this shows how you can do this in just a few lines with like minimal memory cost. So how do you do this? You install Qiskit 1, just the runtime. Pretty straightforward here. I think all of you are capable of doing this. And the tutorial will walk you through mapping the problem to quantum circuits and operators first. And so if you go to this paper, you can actually see the circuits that are run. You can build this yourself one by one. We typically ask people to just fill this in terms of building this transverse field icing model circuit. You can build this ladder structure over these alternating layers of qubits, and you can build these circuits. To make things just a little bit easier, we can make mirror circuits where we compute and uncompute. We can use built-in circuit functions for creating the inverse of these circuits here. And so now you apply U inverse, you should end up back in the all zero state. And then we can just measure like how often we get back to the zero state as a quick check for how noisy this experiment was. Yeah, and then we can bind the angles to match what we did in the utility experiment. This is where you choose the observable. And so here we're using the sparse poly op. Let's say that your goal is to measure all the single qubit Z operators. You can just write a quick script to create them all, Z, I, Z, I, etc. 100 of them. Because they commute, they are automatically simultaneously measured on the device, unless you say you don't want that. And so that's also a nice little helpful thing that's just wrapped up in the estimator. If you want to generalize to the 2D case, you're going to have to copy down this coupling map for the 2D topology of the device. On the device, the minimal graph coloring is 3. And so you need 3 separate layers to interact all the qubits pairwise with each other. And so you can build a circuit in the same way by passing these layers. And so that's the introduction to Qiskit. Are there any questions in that before I hop into the next half? No? You guys gave me a surprisingly easy time. Okay. So with that structure now, we have Qiskit patterns. Like what else are we doing more from the research side to enable bigger, better quantum calculations on these devices? And so that appears in something we're calling Qiskit add-ons. These are meant to be modular. They're meant to help you do certain steps of the patterns more easily. They're supposed to be composable and all that stuff. So just to review, we have mapping, optimizing, executing, and post-processing, primarily handled through the circuit library, transpiler, primitives, and this quantum information package, respectively. And today I want to talk about 3 of these add-ons. MPF, OBP, SQT, just letters. MPF stands for multi-product formulas. I'll explain what that is in a second. OBP stands for operator backpropagation. You can think of this as like a Clifford perturbation theory to minimize the depth of your circuits or to shorten the depth. And there's SQD, which is this sampling-based quantum diagonalization. This is the exact same method that Osama presented about earlier, also wrapped up so you can use it on other molecules of interest. So I'm just going to walk through each one of these, give you a quick sense for why you would expect them to be helpful in your workflow, show you kind of how where the knobs are that you can tune. And I will also be pointing out places where I think there is room for method development, where we've obviously chosen some heuristics. And so if this is of interest to you, I encourage you to jump on it and build from there. So the first thing I want to present about is the multi-product formulas. And so we all know, and we've heard this many times, that a quantum computer can do time evolution. We often do trotterization for near-term circuits, but it picks up these algorithmic errors. So you do a first order trotterization naively, you get this delta t squared error and all the way up. And so the idea of multi-product formulas is to reduce this algorithmic error, reduce this trotter error by doing a weighted combination of several trotter circuits, right? So like, where does this fall in the family of time evolution circuits? It's like, related to the LCU method, except having ancillas and all this other crazy stuff that requires a lot of resources. In one circuit, you break it up into multiple circuits. It has a relationship, not quite with zero noise extrapolation, but in the sense that there's an extrapolation you do to the 0 time step limit. So that's kind of where you can think about it if you know about these methods. And so the computational trade-off is that you have to generate this small set of circuits with increasing number of trotter steps and extrapolate. And basically, any case you have trotter formulas, you can use this. So I guess, variational circuits based on like UCC where you trotterize these terms, you could use it, time evolution, anything like that.